I am Arthur, professor from the Federal University of Rio Grande do Sul, located in the south of Brazil. So it was a long trip from there to here. And I'm here to present the work we are developing in our parallel and distributed processing group in collaboration with some partners from NVIDIA, ITA, also from Brazil, and the oil and gas company Petrobras in Brazil. So, well, we have seen that modern HPC systems, they are executing a lot of applications that are data-intensive parallel applications. And we have big data applications, we have machine learning and oil and gas company. And they are executing these applications because of the power processing capability. And simultaneous to this, we have a power concern because we need to keep these machines operating at full capability to execute the applications. And instead of only improving the performance of these applications, you also need to care about the power consumption. Therefore, we need to improve the trade-off between performance and energy consumption for these systems. Well, as these machines are heterogeneous in terms of CPU and GPU, one point that we can optimize is the data movement between the CPU, system memory, and the GPU memory. So normally when we are parallelizing an application and executing on these systems, we start allocating the data into the system memory, and then we need to move this data to GPU memory and to compute on the GPU so we can leverage the potential of processing units. And we need to do it several times during the execution of the application. So in this way, when we are doing this kind of implementation, the software developer is responsible for managing this data movement in the way that it needs to choose the way to execute the application, how the data will be moved using synchronous, asynchronous communication, will it use prefetch or no prefetching using. So it needs to do that to achieve performance and energy goals. Well, one solution that helps the process of programming these applications on heterogeneous systems is using unified memory. So it simplifies code development in this kind of systems by providing a shared memory space where both CPU and GPU can access this memory. And in this scenario, the programmer doesn't need to care about the data. So it doesn't matter if the data is in the physical memory CPU or in the GPU, because the runtime will take care about the data movement. So I can concentrate my efforts on other parts of the code. So in this scenario, the programmer sees this unified memory, and the data that I am allocating using for example, in NVIDIA, the CUDA malloc managed, the runtime will take care about moving this data from the physical memory from the CPU to the physical memory from the GPU. Well, however, the software developer needs to set up unified memory parameters so can deliver performance for this application. What I mean by this, well, it can use prefetch operations to optimize this movement. And we have seen in some papers and some works that still, if we do a fine-tuning in the implementation of data movement where the programmer is responsible, we can still get better performance than the unified memory. So given this in consideration, this work has the following contributions. We have evaluated the impact of unified memory on the performance, energy, and the energy delay product of a reverse time migration model. And we have considered different generations of NVIDIA GPUs, ranging from the Pascal to the newest Grace Hopper chip. So here is the agenda of this presentation. I will give a brief background about the Fletcher modeling, which is the application that we are using, then methodology, the evaluation, and conclude this talk. So the Fletcher modeling, well, I will try to give a brief explanation about the seismic survey. Although I am not from this research field, I will try to explain this to you. So let's consider that we have a chip, then the sea surface, the ocean floor, the geological interface, and then the trace that we can get. So there is this equipment that emits seismic waves from the ship that will reach the ocean floor and geological interface, and it will return And the towed cables here will detect these returning waves, which will produce this trace that is responsible for illustrating the subsurface through each wave emission. And as the ship moves, so it can periodically emit seismic waves so we can have the full underground mapping. So what the Fletcher modeling does? Well, it simulates this kind of waves, acoustic waves, in a 3D TTI grid. And each point of this grid models a real-world point with properties like pressure, direction, density, velocity, and well, how it is implemented. This version is the hand-tuned version that we developed for the Pascal microarchitecture. So this was very, very fine-tuned for the Pascal. And from that version, we are experimenting with different GPUs generations. So it starts by initializing the grid, so with the parameters X, Y, and Z that we have here. Then it initializes the propagated pointers, here represented by the red point. Then in the hand-tuned version, we allocate the data using CUDA-malloc function. So it allocates the data. Then after each CUDA-malloc operation, we copy the data to the device by using the CUDA main copy async operation. So as soon as we finish the CUDA-malloc, for each operation, we do the CUDA main copy async. Then for each iteration of the wave propagation, it first changes the intensity point device in the grid with a kernel, CUDA kernel. Then it does the kernel propagate, which is the main operation of this application. So all of this is performed on the GPU, so there is no operation on the CPU at this time. Once the kernel propagate finishes, we update the pointers with the grid in the system memory from the CPU. And we do this because at each time there is a threshold that it will write this status of the weight in the HD or SSD. So it iterates until the end of time of simulation, which is a parameter for the input of the application. Well, this is the hand-tuned version. And when compared to the unified memory, what we can see here is that instead of allocating data to device through CUDA-malloc and using the main copy async operations and to update the pointers, we are leveraging all the functions from the unified memory. Okay, so we use the CUDA-malloc manage the operation, and then we use the main prefetch async operation to copy and to move this data while we are doing CPU operations. And that is the main difference between the hand-tuned version and the unified memory version. Also in this version, we have tuned the parameter configuration, the runtime executions of the kernels, choosing the number of blocks, number of threads per blocks through a design space exploration. Well, to evaluate, we have considered 11 different grid sizes, ranging from 88 to 408, which is the size that we can fit in all the GPUs. We consider 5 different generators of NVIDIA GPUs, and here is important to note that we are using the x86 as a host for the Pascal, Volt, Turing, and Ampere GPUs. And for the Hopper, we are considering the Grace Hopper superchip. And here is a special acknowledgement for the NVIDIA, because the experiments were performed on pre-production engineering samples of the Grace Hopper 200 superchip modules provided by NVIDIA. Each configuration and on GPU was executed 10 times, and we measured the energy through the NVIDIA SMI. So we start showing the performance results here, and before, let me just explain how the plots are organized. So we have the results, each bar and each color means a different GPU. So Pascal is the green, Volta, Turing, Ampere, and Hopper for each grid size. And all the results are normalized to the version that is the hand-tuned version. So 1.0 means that the result of the unified memory is equal to the non-unified memory. Okay, so values below than 1.0 means that the unified memory version improved the performance over the non-unified memory version. So the main point here that we can see is that for all executions on Pascal, the hand-tuned version will deliver better performance than the unified memory version. And here, it may be an interesting point because the version that we are using is very well optimized for the Pascal architecture. So we got the same implementation from the Pascal and run on different GPUs. Okay, but we can see that across different generations, the unified memory has improved the performance of the application. And in the, not saying the worst case, but the hand-tuned version was able to deliver up to 20% better performance on Pascal. And on the Grace Hopper, by using the unified memory version without modifying any part of the code, so it's the same code version, we were able to get about, it's 63%, not 73%. It was a mistake here. And the main parts of these improvements can be related to the improvements on the software and hardware layer. For example, the PCIe bus speed that has changed across the generations. Well, considering the energy consumption, for most of the GPUs, the hand-tuned version delivered lower energy consumption than the unified memory version. And in the worst case for the unified memory version, it was 31%, it spent 31% more energy than the non-unified version. But on the Grace Hopper, we have about 42% of energy improvements when compared to the hand-tuned version. When consider the EDP, which is the trade-off between performance and the energy consumption, only one metric. So most of the results are better for the unified memory, mainly on the Grace Hopper. And on the worst case for the unified memory, it was 43% worse than the hand-tuned version on Pascal, but 78% better on Grace Hopper. Again, we did not any change on the code. It's the same code that we are using on Pascal, we are using in the Grace Hopper. So it's not optimized for Grace Hopper, it's for all GPU generations. Because the objective here is to have the same code and what's the behavior of all the GPUs by not changing the code or not optimizing the code. So when we compare the best result achieved by Grace Hopper to the worst result achieved by Pascal, we can improve the DP by up to 85% across the generation, from the unified memory on Pascal to the unified memory on Grace Hopper. So in this work, so we have evaluated the performance, energy consumption, and ADP of the unified memory mechanism on the oil and gas application. And the results indicate that the unified memory has significantly improved across the GPU generations. And as a future work, we plan to compare the results with other solutions and also to improve the range of architectures that are being used. So a special thank to NVIDIA, to the NDA Early Access Pre-Production Systems, to Grids 5000, to the access to the machines, CNPq, CAPS, that are Brazilian agents, and also to Petrobras, the oil and gas company that we have this project with them. So a special thank to them. And thank for your attention and come back from the lunch and not sleeping. And I am open for questions. Thank you.
And we do have time for a few questions, actually. So, what we got?
Yes, I was looking at the performance results. What order of space and time were you solving for the migration that you were doing? Because that makes a difference in how much data is transferred. If you're using small stencils, then you don't transfer, then there's enough memory in the GPUs. But if you increase that order to something, you know, high up, it's more data movement.
You mean data from here or?
Yeah, I was just wondering what order, so what stencil size? Are we using the same stencil size, obviously across all of them because they're the same code, but what stencil size were you using?
It's a 5 stencil.
Thank you.
Yes.
Thank you very much.
Thank you.
Any other questions?
There.
Yeah, thank you for the presentation. I mean, you are comparing, other generation didn't have, they had the PCIe, but the newer generation with the GH does not have PCIe. So how much of the uplift you are getting by having that big pipe connecting Grace and a Hopper versus previous generation was PCIe Gen 4 or Gen 3 or Gen 2, which was very low speed, like Gen 4 is about 32 gigabytes a second. But the newer generation with the Grace and the Hopper is 400 plus, right? How much of uplift do you think you are getting from that versus the real Hopper performance?
Well, I don't know how much because I would need to execute to see the performance results. So we don't have access to this machine to try. So unfortunately, I don't know how will be the numbers. But yes, most of these improvements because of the chip-to-chip communication.